Hey guys, so today I'm going to go over background 5 capacitors. Capacitance is defined as the ratio between the charge and the electric potential between two conductors. That might sound a little bit silly. I'm saying capacitance is the ratio between the charge and the electric potential between two conductors. So just to talk about where this comes from just for a little bit. If we have one conductor in space and then a second conductor in space, right? And they both have some charge on them, so I'll put maybe some positives there and some negatives on here. Then the electric field lines will point something like this and then end up over there. And, I don't really know. These lines are kind of made up, but it'll look something like that. Here, the electric field, as we talked about before, is 0 within the conductor for both of these. And the electric field is perpendicular to the conducting surface for every single electric field line. So this is very important. So if the idea is if I deposit more charge onto each of these conductors, so I'll double the charge over here. So instead of 4, now we have 8. And then instead of 5 negatives here, now we have 10. So the idea behind capacitance is that when I double the charge on both, the direction of the electric field lines stay exactly the same because the electric field will remain 0 within the conductors and the electric field will remain perpendicular to all the surfaces of the conductors. But the electric field outside will now be 2 times stronger than the original electric field. And all the charges have also doubled, right? The N is for new. So the new charge is 2 times the old charge for both of these. So the whole idea behind capacitance is that the charge is proportional to the electric field between conductors. If you have two conductors, the charge deposited on these conductors is directly proportional to the electric field between the conductors. And that is because we need the electric field to remain perpendicular and to remain 0 inside. And there's only one formation of the charges in the conductors that allows this to happen. So when we deposit more charge onto a conductor, the charges will go into the same formation as they were before, just more of them. And the electric field will stay in the same formation as before, just a stronger electric field. And so they remain proportional. If the electric field between them is stronger or doubles, then the voltage between them doubles because voltage is delta X times E. So if the electric field doubles, then the electric potential doubles. So the idea is that since the charge and electric potential are proportional, then we can write a constant of proportionality, which is the capacitance. So that's what capacitance is. It's the constant of proportionality between the charge and the electric potential. So a capacitor is 2 conducting parallel plates with an insulator between them. The capacitance of a capacitor can be calculated using the equation capacitance equals epsilon 0 A over D. So let's say you have 2 parallel plates. They have an area of A each, and they're separated by a distance of D. Then capacitance equals epsilon 0 A over D. That's pretty straightforward, nothing really there. So maybe here I have a battery. Connected to a capacitor. So battery has the one side longer than the other. That's how we know it's a battery. Capacitors have both sides the same length. In this circuit, here the capacitor will have the same electric potential across it as the battery. So we'll have also plus 5 volts across the capacitor with the same polarity as the battery, with the left side being the positive and then the right side being the negative. The energy stored by a capacitor is energy is stored within the electric field. So if we have like an electric field here, this is all energy, and the amount of energy stored is, this is energy of capacitor, is 1/2 the charge times the electric potential between the plates, or 1/2 using Q equals CV, then we have 1/2 CV squared, and this is also the same as 1/2 Q squared over C. These are 3 equations for the energy stored within the capacitor. RC circuits and charging capacitors. So let's say we have a battery here of 10 volts, and this is 10 ohms. It doesn't really matter. And this is 1 farad. The units for capacitance is farad. And I'll make this bigger. So what happens here is when we first start the circuit, so initially everything's off. We show this with an open switch. Initially, the switch is open, so there's no current flowing in the circuit. The second we close the switch, so I'll say this is t equals 0 minus, meaning right before time 0. That's what the minus means. Then we close the switch, so this is t equals 0 plus right after the switch closed. Right after the switch closes, then what happens is we get a current. How much is the current is the big question here. Using KVL, so because no current has flowed yet, we just closed the switch, no current has gotten the chance to flow, then the voltage across the capacitor is still 0. Right? Because, so 0 volts, I wrote plus minus, but it really doesn't matter because it's 0 volts. And this is because no current has gotten the chance to flow through the circuit yet. If we do KVL, then we get, moving here, we get plus 10 volts. And then here we drop some voltage across the battery. And that voltage is going to be 10 times I times the current. And then we drop some voltage over the capacitor, which is 0, because we know the capacitor has no voltage because it has no charge, because no current has flowed through yet, so no charge has reached the capacitor. And then we solve for the current is 1 amp, just straight from that equation. So the current is 1 amp through the circuit, and so that's the rate of the movement of charge, right? Current is the rate of the flow of charge. So we now have 1 amp of current in the circuit. Okay, so after a little bit, so let's say now we're at time equals 0.5, and that number is completely made up. I have no idea, but let's say we're at time 0.5. So some current has flowed through the circuit. So that means we ended up with some positive charge over there and some negative charge over there. Note that I'm putting the same amount of charge on each plate because any positives on the left will attract negatives to the right side plate. And so now we have some voltage across the plate, and I'll make up another number, maybe 5 volts across the plate. Now that we have some charge on the plate, we get some voltage across the plate, right? From Q equals CV. If charge is 0, then the voltage is 0. But because we now have some charge, then this is not 0, and so the voltage is not 0. Anyway, so now we have some voltage across the plate. And doing KVL again, we have plus 10 as we pass through the battery, and then minus 10I as we cross the resistor, and then minus 5 volts as we cross over the capacitor, moving this way, and this is equal to 0. So now we have a current of I equals 0.5 amps. So now the current is flowing slower, and we will charge slower. So here, capacitor charging faster. This is because we have 1 amp of current. Here we have the capacitor is charging slower because we have 0.5 amps of current. So remember, current is the movement of charge. So if charge is moving to the capacitor faster, it is developing a voltage faster. It is charging faster. If current is smaller, then the capacitor is charging slower. Then we wait another second. So here we're at t equals 1.5 seconds now, and we're at 10 ohms. And now the capacitor has a voltage of 8 volts across it. And again, all these numbers are made up. Right now I'm really just explaining how the whole thing works. So now let's look at the current again. We have, as we pass through the battery using KVL again, we have 10 volts. And then as we pass by the resistor, we have minus 10I, where I is the current. And then as we pass by the capacitor, then we have minus 8 volts equals 0. And this gives us I is 0.2 amps. And now the capacitor is charging even slower. The way this looks on a graph is if we have the voltage across the capacitor as a function of time, a graph here, the maximum voltage after a really long time, the capacitor will reach 10 volts. It'll be the same as the battery and will have no current through the circuit. So I'll actually show that real quick. So as the time goes on, so here we have time is infinity. It's been infinite seconds. Then we've had enough current such that the voltage across the capacitor is now 10 volts. So KVL again gives us 10 volts, increase right there. Then minus 10I, and then minus 10 volts across the capacitor. And this gives us I equals 0. So once the capacitor has reached 10 volts, the same voltage as the battery, then our current drops to 0. And so there's no more current flowing through the circuit, it's just a dead circuit now. Or stagnant circuit. So what this looks like is initially it's charging really fast, the voltage is increasing really quickly, and then it starts to level out. It charges slower and slower, and eventually we reach that flat line at 10 volts. And so the equation for this graph for the charging voltage is V voltage across the capacitor is the voltage maximum, which here is 10 volts, times 1 minus e to the t over RC. 1 minus e to the negative t over RC. So using our numbers, we have voltage across the capacitor is 10 volts times 1 minus e to the negative t, and then the resistance is 10 ohms, and our capacitance is 1 farad. So the equation for our graph is VC equals 10 times 1 minus e to the negative t over 10. For a discharging capacitor, it works the exact opposite way. So initially we have a circuit, and this capacitor has 10 volts across it. And this is right after the circuit is closed. And then we'll have, so this is the positive side of the capacitor, here there's the negative side of the capacitor. And so the voltage across the resistor is the same as the capacitor using KVL. We have here we have a drop of 10 volts. And then here we have an increase of, this is 10 ohms, 10I, and so we get I equals 1 amp. And then as the voltage drops, then we get, eventually after it loses some charge, then we have 5 volts. Then the current now becomes, here we have a drop of 5 volts, and then here we have an increase of 10I, and so here we get a current of 0.5 amps, and it starts to charge slower or discharge slower and slower and slower. So it starts at 10 volts, it approaches 0 volts eventually, and the rate that it loses charge, it decreases and it gets slower and slower and slower. So here we have 0 volts, and then here we have 10 ohms, and there's no current in this circuit. So very similar but opposite. So the graph for this is actually something like this, and it approaches 0. Here we have T voltage across the capacitor, and the equation for this graph is VC equals Vm times e to the negative t over RC. So for our problem specifically, it's VC equals 10 times e to the negative t over RC, where R is and the C equals 1 farad. So like that, and that's our equation for the voltage across the capacitor as a function of time. Now that's the voltage across the capacitor. How about the charge of the capacitor? Well, using our equation, Q equals CV, we can multiply this equation. Here by the capacitance on both sides. So then we have C times VC equals C times Vm times 1 minus e to the negative t over RC. But C, the voltage times the capacitance is charge. So we have charge of the capacitor is equal to the charge maximum times 1 minus e to the negative t over RC. And same for a discharging circuit, we would end up with the charge of the capacitor is equal to the charge maximum times e to the negative t over RC. So that's our charging and discharging cycles. That's the way it works, and that's how it works. Now this term RC is quite important. We call that the time constant. So these equations can be written as VC equals Vm times 1 minus e to the negative t over tau, and VC equals Vm e to the negative t over tau. And again, this is our charging circuit, this is our discharging circuit, and the equation for tau is RC, the time constant. And tau has units of seconds because it's a time constant. But after RC seconds, after one time constant, then our voltage across the capacitor is Vm times 1 minus e to the negative tau over tau, which is Vm times 1 minus e to the negative 1. Now, 1 minus e to the negative 1 is 0.63. For a charging circuit, after one time constant, then we've reached 63% of our final maximum voltage when you're charging a capacitor. For a discharging capacitor, with Vm times e to the negative t over tau. So after one time constant, after RC seconds, then we have Vm of e to the negative tau over tau, which is Vm to the negative Vm times e to the negative 1, which is 0.37 Vm. And this is a discharging capacitor circuit. So after one time constant, for charging capacitor is charged to 63% of its maximum voltage, and for discharging capacitor after one time constant has lost 37% of its original voltage. So here our time constant is 10 seconds. So after 10 seconds, let's see, that's right here, and this maximum voltage was 10 volts, then now right here at 10 seconds we're at 3.7 volts, because we're at 37% of our initial charge voltage. And here for this one right here, this is at 10 seconds, we're at 6.3 volts across the capacitor. So it's important to know those values, the 0.63 and this 0.37, or 63% and 37% after one time constant.